Welcome back to Intro to GameTank Programming. Today we'll import and draw animation frames from a bitmap image. We'll also read inputs from the gamepads and use them to move an animated object. Many art programs can produce suitable bitmap files. I use a Sprite. The important settings are to use images 128 pixels wide and at most 128 pixels tall, with the indexed color mode. The palette should be set to GameTank.act, which can be found in the GameTank emulator/MSYS folder. The GameTank interprets each byte as a description of hue, saturation, and luma, also called luminosity or brightness. Hue describes which color of the rainbow is being shown. Saturation describes whether the color is vibrant or faded all the way to gray. Luma describes whether the color is dark or light. The effects of these three settings can be observed in the color palette on the left. Note that certain colors are repeated. This is because the hue bits have no effect when saturation is 0. Also notice how the lightest colors lose a little saturation. To conveniently produce image data, we'll take advantage of the structure of bitmap files. In an 8-bit bitmap file, each color is also represented by a byte. But unlike on the GameTank, a given byte value means little by itself. Bitmap files include a palette table, which is a list of colors described with RGB values. When displayed, each pixel value is looked up in the palette table to determine the color that is shown. GameTank.act is useful because it makes a bitmap file approximate the image the GameTank would show using the same image data. So we can convert this bitmap into the GameTank format by simply cutting off the header and the color table. When you save your image to the Hello GameTank folder, make sure to save with the .bmp file extension. You should also flip the image vertically, as in upside down, before saving, as bitmap files store pixels from the bottom up. We're done with our image, so let's switch to VSCode. To cut the header from the file, we'll use a simple Node.js script that I'll link in the video description. The script takes a specified number of bytes from the end of a file and saves it as another file. I'm using 16,384 here because the image is 128 times 128 pixels. Now, 16 kilobytes is way too big for the 8 kilobyte cartridge we're targeting. Compressing the file with Zopfli will fix this issue. Wow, the deflated file is only 348 bytes. Zopfli did very well here because the image was mostly empty. The downside of this approach is that the data must be decompressed before it can be used. zlib6502 is ideal for this task. For convenience, I've supplied a pre-compiled binary in the GameTank emulator repo. Just copy inflate e0000200.obx from asm/tutorial/assets. Finally, we'll begin coding. We'll include these two binary files into our code. The .inkbin directive will include an external file into our ROM. Inflate e1200.obx will be included after the inflate label. Sprites.gtg.deflate will be included after the sprites label. Before we can extract the data, we'll need to initialize the GX and GY counters, then disable the blitter so we can access graphics RAM directly. But first, a little cleanup in the reset section. This setting for DMA flags will be different between our background and foreground draws. We'll move it from reset to immediately before each draw setup. Then we'll change the width and height of our foreground object to 16. While the screen is only 128 pixels wide and tall, the space that contains sprite data is 256 pixels wide and tall. In direct access mode, only one quadrant of this area is accessible at a time. Which quadrant is determined by the 8th bit of the GX and GY counters. When the system is powered on, there is no guarantee that the counters will hold any specific value. The only way to update these counters is by running a draw operation, so we set up a single pixel draw with the GX and GY registers set to 0. Next, we'll set DMA flags to a mode where the CPU can directly read and write graphics RAM. The important bits are the first and sixth, which should be set to 0. The pre-built inflate routine looks for parameters at addresses F0 through F3. We'll define the name inflateZP as F0. I'm commenting F1, F2, F3 here to remind myself that these addresses have been reserved. The first 2 parameter bytes indicate the location of compressed data. Since we can't copy a 16-bit address all at once, the less than and greater than symbols are used to select an 8-bit half of the 16-bit value. The last 2 parameter bytes indicate where the decompressed data should be placed. We'll provide hex 4000, which is the same address as DMA VX, but points to VRAM or GRAM when the blitter is disabled. Instead of writing hex 4000, though, we'll label this as frame buffer and define the label higher up afterward. JSR stands for jump to subroutine. Like jump, it will move execution to a specified label. In addition, it saves the current code location like a bookmark. We can return to it later with RTS, return from subroutine. Here, we'll give it the inflate label that we created earlier. For the DMA flags before the second draw, we now want the 4th bit to be 0. This bit controls color fill mode. When it is set to 1, the blitter only draws rectangles with the color set by DMA color. When it is set to 0, the blitter will draw images from GRAM instead. At this point, if we recompile the code, we should see a character take the place of the blue square. Since we forgot to update the bounce code, the character goes a little bit off-screen and wraps to the other side. We'll just lower the maximum x coordinate by a few pixels. Now that we have a character, let's make this interactive by reading controller inputs. We'll need a few more definitions at the top of the file. Gamepad 1 and Gamepad 2 are at hex 2008 and hex 2009. Even for a single-player game, both registers are needed. We'll also define player X and player VX to give names to memory slots 0 and 1. Buttons pressed will be used to track the buttons that were last read from a controller. Finally, some input mask constants will be useful for interpreting the bytes read from the controller port. To read player 1's controller, first read Gamepad 2 and then Gamepad 1. Each gamepad has a select flag which toggles each time it is read, and is reset when the opposite controller is read. The first time Gamepad 1 is read, it gives the status of the up, down, A, and start buttons. The second time, it gives the status of up, down, left, right, B, and C. We're only interested in directional buttons for now, so let's read it twice and use the second value. The controllers use 0 to mean pressed and 1 to mean not pressed. It's a bit easier to read them the opposite way, so EOR, or exclusive OR, with constant hex FF, will flip each 0 to a 1, and vice versa. If no buttons are pressed, we want the player to default to not moving, so we set player VX to 0 first. To check if left is pressed, we perform a binary AND with input mask left. Then we'll branch if the result is not equal to 0, moving to the input left label. If the branch is not taken, then we load buttons pressed again, binary ANDing it with input mask right this time, and BNE to input right. If that branch is still not taken, then we'll jump to after inputs to skip both input left and input right. Input left sets player VX to hex FF, equivalent to -1, then jumps to after inputs to skip input right. Input right sets player VX to 1. It does not need to skip any code. Now when we compile the program, the player should move left and right when we push the corresponding buttons. However, nothing stops the player from rolling off the left or right edge of the screen. The problem is that our code for checking edge bounces gets overridden by the inputs. We can move it into a subroutine, then call it in between the inputs and player VX being applied to player X. Now the player cannot pass the left and right screen boundaries. Let's finish off the session by animating the player. Add definitions to track variables for the player's current frame number and which animation should be playing. This sprite sheet separates the animations by rows, so we'll call these player anim frame and player anim row. Before drawing the player, we'll check their velocity. If either player VX or player VY are not 0, then jump to do anim walk. Otherwise, we'll fall through to do anim stand, which simply sets the frame and row to 0. Do anim walk adds 16 to the frame number, then ands it with 48 to ensure that it stays a multiple of 16 less than or equal to 48. It also sets player anim row to 16. We'll update the drawing setup so that DMA GX is set to player anim frame and DMA GY is set to player anim row. The player now cycles through their walk animation whenever a direction is held. You may have noticed that some code was added to enable vertical movement. By copying your code for horizontal movement and adding some definitions, it shouldn't be too hard to add this on your own. Think of it as a little extra challenge to try. I'll link the code shown in the description, including vertical movement, as well as an extra bonus.